So we continue. Just a quick announcement. So there's one lecture and then have lunch. Just before we begin lunch, we're going to take a group picture. So when we're done, I'll say it again. When we're done, we go downstairs and gather and take a picture, and then you can eat. Okay, so there's a slight switch in the schedule. So Kim Bymack was supposed to talk, but Gia Shan is switching with him. So Gia Shan is from Cornell. Both of them are from Cornell. Doing some very exciting work these days, and I'm eager to hear what you have to say. But thanks for coming. Appreciate it.
Okay. So I got this assignment to talk about gating and the spectroscopy of semiconductor moire materials. I actually don't know what I am exactly supposed to do. So I put something together without knowing the audience. So those of you who would like to think yourself as a physicist, could you please raise your hand? Okay, thank you. So I would assume the rest will be chemists or engineers. Please stop me if I become totally impossible to follow, okay? So as I said, I'm going to talk a little bit about some basics of optical characterization of this class of materials. And I'm sure you have seen this already. Just the definition of moire materials, it's large scale interference patterns. And we can put two same materials together with some twist, or two different materials with slight difference in terms of lattice constant. You can also get this moire pattern. And here is one example from our group at Cornell. So what you are looking at here is moire bilayer made of moly telluride and tungsten selenide. And this is 60 degrees. And the color here, heavy elements showed up more. So this is a transmission electron microscope image. So what we can learn from this image is that you get those periodic patterns because of the lattice mismatch between the two materials. And if you read the scale here, it says 2 nanometers. So the period here is about 5 nanometers. And this is determined by the lattice mismatch between the two materials. It's about 7 nanometer and the usual lattice constant of those TMDs. So here is kind of a very simple model to determine the moire periods when you put, for example, homobilayer or heterobilayer together with some twist angle. And as you can see here, the red one is for heterobilayers, and the yellow one is for homobilayers. And you can see it's very sensitive, the moire period, to the twist angle if you have 2 identical layers with some twist, right? And this also teaches us that if you want something uniform, not very sensitive to twist angle disorder, then maybe the choice of heterobilayer will be a better one. So because the lattice constant is not very sensitive to the twist angle when the angle is relatively small. So for the rest of my talk, I'm going to focus on this case, putting 2 different semiconductors on top of each other, either with some small twist or at 0 or 180, which is 60, 120. It's the same thing because the rotation symmetry. Okay, so why are we interested in this class of material? You are going to hear a lot more from Professor Kim Bymack tomorrow on the prospect of using this class of material as a quantum simulator to study other important fundamental questions in condensed matter physics. How do we synthesize them? I use the word synthesis very broadly. Physicists view, we exfoliate and stack. Okay, how do we fabricate those materials? And I hope you already learned yesterday from Professor Yu Zhu's talk. Am I correct? Okay, yes. And today I'm going to focus on optical probes. How do we use optical spectroscopy to study this class materials? So let me get started. So first, I would like to review a little bit of optical properties of this monolayer transition metal dichocalcogenides. You probably already heard a little bit yesterday from Professor Yu Zhu. I'm just going to summarize a few key points which are relevant to the study of moraine materials. So the first thing is very strong light matter interactions in this class of materials. Here is the structure of monolayer TMD semiconductors. David already gives a very nice introduction of this class of materials. So what I would like to emphasize is that, in the limit of a monolayer, this class material is a direct bandgap semiconductor. And the bandgap occurs at a K and a K prime point of the Brillouin zone. So you can think of this just as gap to graphene. So the gap size here is on the order of 1 to 2 electron volts. And this material has a heavy metal, so has very strong spin orbital interaction. And what that spin orbital interaction does is to split those bands into spin up and spin down. So those bands are all spin split. At the same time, you have time reversal symmetry preserved. So if you change this K value to the K prime or minus K, some people would like to call value, the sign is switched. So spin up becomes spin down, K becomes negative K. So what we call this spin value locked. So in other words, you can think of this, each copy is spin polarized, right? But the other copy has opposite spin and value. So they just cancel each other. Time reversal symmetry is preserved in this case. So because it's a direct bandgap semiconductor, you can have very strong interaction with light. Let's take a look at some measurements. So this is a spectrum I borrowed. I should have put a reference here. So this is the absorption spectrum of moly sulfide on top of some transparent substrate. So the y-axis is absorbance and the x-axis is the photon energy. So I would like you to pay attention to two features, which I call the A and the B, those very sharp resonances. And they correspond to optical transitions from the upper valence band to conduction band, and the B corresponds to the lower, the spin split valence band to the conduction band. So because the valence band, the spin splitting in this class material is very big, a few hundred milli-electron volts. And for the electron bands, it's relatively small, like tens of milli-eV. So this splitting tells you about this pretty much, the valence band energy splitting. And if you read from the spectrum, it's on the order of 300. And for some elements will be 500-ish, 400, 500 milli-electron volts. So when we work with marine materials, we are very interested in the low energy physics. Therefore, you don't need to worry too much about the second valence band. So pretty much let's forget about the B exciton. This is not something we need to worry about because it's a few hundred millielectron away from the lowest transition. And then the inset shows the detail of this peak. It has this A resonance and some shoulder. And then later, when we improve the material, you see separate peaks. So there's something else going on. So I would like you to get a few messages here. The first, if you just read the y-axis, 0.1, 0.2, and that's enormous for a monolayer material. It says like, you can absorb like 10% of light just within a single sheet of those materials. So that's first. Second is that for different TMDs, this resonance occur at different energy. So if you probe the heterobilayers using optics, you will be able to layer resolve. You can read each layer separately because there's different energies. And the third thing, I would like you to pay attention to the peaks. So we are dealing with two-dimensional materials. For those of you who remember STEPMAC or solid state, joint density state in 2D should follow STEP, right? So if it's really like a 2D absorption, the feature should not look like a peak. It should look like a step, but we see very strong peak. So there's something else going on. So let me go to that. So that's something else is the electron hole Coulomb interaction. We call it excitonic effect. So let's imagine you have a single sheet of a semiconductor. Optically, you excite positive and negative charge. And because the electrical field lines are so much outside of this material, so the screening is very weak. So in that case, the binding energy between the optically excited positive and negative charge is very big. And we and others made measurements, this binding energy can be as large as about half electron volts. And that's why you see a sharper peak instead of step, okay. We can look a little bit more into this, So this is like early sample. You see not much of like details, but if you have better sample, you can actually see lots of features between A and B. And the reason is because, you can think of the excitons as two-dimensional hydrogen atom. So they're in some 1/r or modified 1/r potential. Then you can think of this as like a Rydberg atom. So you should have Rydberg series. Indeed, Rydberg series has been observed. So this is just a cartoon, which shows, the dominant 1s exciton peak, and you have 2s, 3s, and until you hit the continuum, and continuum is somewhere there. So every higher excited state will be weaker and weaker, right? So this is a cartoon. In measurement, this is from monolayer of tungsten selenide. You see a main peak, which is this 1s. But now I have to magnify the 2s, 3s by 5 times. You can see the 2s and the 3s, and then, not anymore. So those are much weaker. And you also kind of notice now the line feature is a little bit different from what I showed you before. Instead of very nice peak, now we see a little bit like a derivative-like shape. And this is because of optics. If you put this monolayer in some stack, And there's a difference in refractive index, you get the interference effect due to the multi-layer structure. So, but the main message is there. You can see the fundamental exciton state and those highly excited states. And then from, for example, this continuum is kind of has very subtle signature. It's hard to tell. So, but from the separation between 1s, 2s, you can roughly estimate the exciton binding energy. Okay. One other property I would like to mention is that those optical transitions are very sensitive to doping. So this is kind of a contour plot. Let's just focus on what's in the middle, right? So this is the case when monolayer molyselenide in this case is charge neutral. And you see this very strong absorption, and this corresponds to that 1s peak. And then you see this faint one, this is 2s state. But now if you push your gate, you electrostatically dope this material, either electron doping or hole doping, you can see that this very strong peak immediately quenched. And you see some redshift one, and then this remaining is like a blue shifted. And this is due to many body effects when you have exciton in the sea of electrons or holes. And this is called repulsive polaron. This is attractive polaron. But the main message is that redshifts become, two features. So if you see something like this, your sample is doped. So this is a very sensitive probe of doping as well. Okay. So now let's get to work. So now I would like to talk about, using those optical probes to study the marine materials, right? So first we put them together in a device. So this is kind of a very typical device structure. We have samples sitting in the middle, and now we have hexagonal boron nitride, both on top and the bottom, as gated dielectric. And then we have field layer graphite as top and the bottom gate electrodes. Okay. And this is how the device looks like. Actually, you have lots of those electrodes, which will allow you to do transport measurements. And I have to say that, making good contacts to those materials is not easy because they have large gap. And that's why optical measurements play a very important role to study them. So this rectangular shape, the whole bar, is where the sample is. So the two gate voltages, you have 2 degree freedom, right? So you can change 2 things independently. So let's just imagine the thickness of the HBN is identical in the top and the bottom. Then in that case, if I put, plus 1 volt here, plus 1 volt here, then the electric fields across the sample is 0. I can change the doping density. But if I make them, one is plus 1 volt, the other one is negative volt, then I will only change the electrical fields perpendicular to the sample. So if the thickness are different, you can make adjustments according to the thickness. So the bottom line is that those 2 voltages independently can tune both the doping density in the sample and also an out of plane electric field. Sometimes you see people call it displacement field. And those 2 knobs can change a lot of physical properties, as you will see later in the talk. Okay, so now we're going to do spectroscopy on this material. So in this particular case, it's a tungsten selenide and tungsten sulfide moire bilayer. And then, we just shine light from top and detect the reflection. The top case is when the 2 layers are quite random at a large twist angle. So you can think of this case as an approximation of two independent, isolated, well, not quite isolated, but two independent layers. And the bottom is when they form moire pattern, which in this case, either 0 degree or 180 degrees. So I want to give you something to work on. Yes.
How do you identify the axes placed?
Oh, okay. So either you missed the talk yesterday or yesterday he didn't talk about it. Okay. So this is very important. So if you just look at the underlying material, right? So each has this honeycomb structure, right? And it's central symmetry is broken. So you can do second harmonic generation from those layers. So you come in with omega and you detect 2 omega. And that is powerful.
Oh.
Yeah, thank you. So that second harmonic generation carries the symmetry of your crystal. So it will know the armchair or zigzag direction of your crystal. So you first do second harmonic on each crystal. You find out which one is armchair, which is zigzag, and then you put the two together. That's how we stack them with target angle at least, and which could be very accurate, you know, half a degree-ish. Okay, so I have some exercise for you to do. Please just look at the top and look at the bottom and tell me the differences between the two. Okay, you see some redshift, is that right? Okay, so you know this occurs this energy and this is shifted to lower energy.
Also some wiggles.
Some wiggles. Okay, so what is y-axis? The y-axis here is doping. So you put a more and more charge. So some doping dependence. Yes, anything else? Redshift, doping dependence.
There's also some new features in the.
Okay, new features showed up around this main ones. Okay. Broadening, yes, very good. So I put down, you know, those four. So those are the things that Moray is doing to those excitons. Okay. So the redshift is because now the two layers are coupled, so there will be something. Okay. Broadening, you know, due to coupling is one reason, or due to introduce extra defect disorder, you know, because the two layers at the twist angle 0 or 60, there'll be atomic reconstruction, other effects. Okay. Those multiple features, what are those? So if you think about the Moray structure, right, we are thinking of periodic potential. When the kinetic energy of the exciton is small compared to the Moray potential, you get those modulations, similar to, you know, what periodic potential would do to electrons. You can think of that effect. And then you have some doping dependence, and not at a random doping, at something, you know. So that's something we need to figure out. So let's just do some simple thing. We're going to blow up this panel and look at it more carefully. So this is just this fundamental exciton feature in one of the layers. And the y-axis is the doping density. And because we know the twisting angle, we know the Moray unit cell density, we can convert this doping density. Well, by the way, this doping density is from the gate voltage and the gate structure, right? You can convert this to the filling factor of Moray unit cell, right? So for example, this line corresponds to 0 doping. This line corresponds to 1 charge per Moray unit cell, and this line corresponds to 2 charge per Moray unit cell. And we see some kind of, enhancement. Remember, I talked about very sensitive dependence of those transitions to doping in the monolayer case. But look, we still have lots of intensity left, even if you dope it up to 1 particle per Moray unit cell. So something else is going on, right? So if I look at the intensity of the transitions and then plot this at different temperatures, and you will see this, okay? And the blue line is at the lowest temperature. So this may remind you of something, like when you cool it down, this peak becomes bigger, right? But if I correlate this with transport measurement, you will see it. So at half band filling, which is 1 particle per Moray unit cell, because there's 1 state for spin up and spin down. So you need 2 particles to fill the band. So 2 particle or full band filling is right here. So this is something like, okay, you fill a band, you got an insulator, and that's from the transport, resistance goes up when you pull it down, right? So this is an insulator, and now absorption goes up. And then at this half band filling, you also got an insulator, and this is something interesting. So to understand what's going on here, I just showed this cartoon picture. So now, because we put this charge into this Moray potential, periodic Moray potential, right? So basically, you make the kinetic energy smaller. You quench the kinetic energy, you get flat band. That's what you heard earlier on Monday, right? So when you have a small kinetic energy and you have a large Coulomb interaction, for example, so you can estimate how big is the Coulomb repulsion if you put the 2 charge at the same site. And this is given by E square, dielectric constant, and also the size of winding function. Right? And this can be on the order of 100 millielectron volts for this particular material. Kinetic energy is small. So in that case, the Coulomb repulsion can localize the charge. So even if you only have half band filled, this can be an insulator, and this is not insulator. And of course, you need an extra measurement to support this really is a mod insulator, but the measurement I showed you supports that this is an insulating state. In terms of the band picture, you can think of the following, when interaction is not important, it's just a single particle picture, I have this band half filled, which should be a metal, right? But now if U is very big, the Coulomb interaction localizes the charge in terms of band, it splits this into upper and lower Hubbard band. And instead of metal, now this is an insulator. And the gap here is determined by Coulomb U. And this explains, what we saw optically and supported also by transport. Okay, so now we know this optical technique is somewhat sensitive, but not as sensitive as transport. But when you cannot do transport, this will give you an indication of what's going on in the sample. So now we would like to look at this feature more carefully. You say, well, at this, you have large intensity, at this point, large intensity, but how about here and here? some wiggle here, but looks like you also have enhancement of intensity, right? And does this mean you also have some kind of insulating state? And if you look at the charge here, this corresponds to 1/3 of the Murray unit cell doped. And this guy corresponds to 2/3 of Murray unit cell doped. So this optical measurement gives us some hint, perhaps something else is also going on, but we do not have sensitive probe to tell. So next, I would like to tell you about this new probe, which we developed recently at Cornell, just to measure something like that. Okay. So I told you about strong excitonic effect due to reduced screening, right? But if you look at it more, like what determines the binding energy of the excitons, you have the usual stuff. You also have dielectric screening, right? So this binding energy is sensitive to the dielectric environment. And in the case of this fundamental exciton, the ball radius is relatively small, on the order of 1 nanometer, and the 2s, 3s becomes bigger and bigger. Right? So how about taking exciton away from the sample, put it somewhere else, and use this as a probe of the dielectric environment? So imagine that now if I put a metallic sheet, some 2D electron gas system, next to my single sheet of semiconductor, I expect the screening to be strong, right? And this will reduce the binding energy and make the absorption weaker, right? But if I put an insulating state next to it, it should not affect the exciton binding too much, and the absorption intensity should still be large. And this will give me some sensitivity to, for example, the correlated insulating state or any other insulating state. So this is the device structure. So now, in addition to sample between the two gates, I want to stick a sensor, right here. And that sensor is just a monolayer of a semiconductor. So in this case, would be tungsten selenide, because high quality crystals are available, grown by Jim Holmes' group, whom you have seen on Monday. And we chose those materials such that when you change doping using those gates, you leave the sensor intact, charge neutral throughout the process. And the doping only goes into the sample. And this you just need to work out the band alignments when you pick your sensor, for example. Okay. So on the right-hand side, I'm showing you a simple example. It's a control experiment where my sample in this case is a monolayer of tungsten sulfide. And those two are the spectrum from my sensor, which is a monolayer of a tungsten selenide. Okay, and you can take the spectrum in a single shot. I just divide them into panels. Okay, so let's take a look at what's going on here. So first, let's take a look at the sample. The y-axis again is the doping density. So initially, the sample is charge neutral. So you see very strong 1s resonance, right? Now I move up. I introduce charge into tungsten sulfide. Then you can see, this 1s exciton is quenched. It becomes weaker, and then the newer feature shows up. So this is the repulsive. This is the attractive photon I mentioned earlier. Sometimes people also call this charged exciton. So this is what's going on in the sample. We know it from optical studies. Now let's take a look at what's going on in the sensor. And the sensor is charge neutral throughout the process. So, and this can be seen from this 1s transition, right? Nothing changes. goes straight. Doping does not change anything. And this verifies that, this sensor is charge neutral. But at the same time, let's take a look at the 2s and the 3s exciton. So this 3s, pretty weak. You don't see this as soon as the sample is doped. But now the 2s, you can still see it because the intensity is higher. You see almost the same feature as here, right? You see this redshift. This is a charged like feature. So as soon as your sample is doped, your sensor develops this redshift. And this will be a very good indication of what's going on in the sample. Okay. And then in this case, it just goes like not much of a dependence on whatever the extra charge you put into the sample. So now what I'm going to, yes, go ahead.
Oh, sorry, why would the influence of Y state only 2s and 3s?
Yeah, that's a very good question. So I mentioned earlier that the exciton ball radius very differently. So 1s has very strong binding energy, so it's very tight. They're small, and the 2s, much bigger. And one thing I did not mention in this setup is that those two sample and a sensor. Thank you for your question. Are separated by a spacer, and we choose the spacer, on the order of nanometer or a little bit more. So in that case, the 1s excitons, they don't see much of what's going on, but 2s, 3s will see a lot of what's going on. So that's why this guy is not too sensitive, but the 2s, 3s, and higher ones should be more sensitive. Yes.
So then follow up, have you have systematically changed the space?
Yes. Yeah. So for example, if you change the spacer to like larger than the ball radius of 2s, then 2s becomes not sensitive, but 3s you can still detect what's going on. But of course, experimentally there's a challenge because 3s is much weaker, signal to noise ratio will be worse, things like that. Okay. So we keep our design such that we fix the spacer on the order of 1 nanometer-ish, and we are going to focus on the 2s only. Okay. So here is this map. So what I'm showing here is the spectrum of 2s exciton resonance in the sensor while I'm changing the gate. And what this gate does is to put more and more charge, electron, or more and more hole into my sample. And my sample is, sorry, it's not here. It's tungsten selenide, tungsten sulfide, moray bilayer. Okay. And I just want you to see the kind of, lots of variations here. So the color, blue means you have strong absorption, strong 2s, and the orange or red means you have relatively low one. So as you can see that at the 0 gate, your sample is charge neutral. You see very strong 2s response, and this is expected, right? But when you dope your sample, either electron or hole, you see the 2s energy is smaller, and then the response is also smaller. And this is what we argued earlier, that the screening can reduce or quench reduce the exciton binding in the sensor. But on top of that, you see some features, looks like this guy, but less prominent. So what are those guys? I converted the gate voltage to filling factor. Top is this is for electron, this is for hole. So we see this peak at the filling equal to 2. That means 2 particles per Moray unit cell. We have a band insulator. And this is something we saw earlier. Right? We saw this insulating state at a filling equal to 1 particle per mole unit cell. This is the half filling, and that consistent with what we think is a mod insulating state. Right? And then in between, you have many of those, and they actually occur not randomly, they occur at some rational fractional filling, like 1/3, 2/3, this and that. Okay, so I'm just going to show them here. So those, 1/2, 2/3, 1/3, 1/5, 2/5, and many more. So our collaborator did Monte Carlo, and those are the stable ground states matching those states. Okay, and later on, there's this very clever STM experiment from the Berkeley group. So they put graphene away from the bilayer, and then those charge puddles, if they form a periodic pattern, that puddle potential should also be reflected on the graphene layer, and then you can do STM on that, and that indeed shows those patterns, predicted by the, okay. So, okay. I don't think I have time to talk about this. So I just want to recap that, we talk about strong light matter interaction and what this can do for us to characterize these marine materials. Now I'd like to switch gear, talk about how to characterize the magnetic properties of those materials. And for this, I would like to remind you of the spin valley dependent optical selection rules. Okay, so it turns out that in monolayer TMDs, light-handedness exclusively coupled to spin valley degree of freedom. So for example, at the K valley, this transition is one-handedness, and then if you go to the other valley, it's the opposite handedness. So now let's say for whatever reason, either because you apply external magnetic field or there's some internal magnetic field, those two valleys are not balanced anymore. So in this case, this guy is higher. So then if Fermi energy goes right here, then this transition will be blocked, right? And only this transition is left. So now if we come in with circular polarized light and look at the difference between left circular polarized and right circular polarized, you will see huge difference in this case. So the difference between the two polarizations, left and right handedness, is called magnetic circular dichroism. So in this particular case, this MCD is linearly proportional to magnetization. So in the case, when you have two valleys are balanced, left and right, they cancel each other, you get a 0 MCD. And in this case, you have large MCD. So MCD is a good way to probe those materials. And again, it's layer resolved because you tune to the resonance, you can look at each layer separately. So this is one example. You measure MCD as a function of magnetic fields. When you don't apply any magnetic field, in this case, there is no magnetization, so it's 0. And when you ramp up a magnetic field, initially it increases linearly with magnetic field, and at some point it saturates. So if you just look at this curve, I can read out two things, right? One is the slope. So the slope is magnetization as a function of magnetic field. So this is nothing but magnetic susceptibility. We don't have like quantitative, but it's proportional to magnetic susceptibility because we don't know how to calibrate in this case. But in some cases, you can also calibrate it. But so let's look at this, when you apply large enough magnetic field, you can fully polarize that way. So this saturation field tells you about the exchange interaction strength. So once you can measure magnetic susceptibility, you can look at the temperature dependence, right? And if we go back to Kittel, so for paramagnets, you measure magnetic susceptibility, it goes like some constant divided by temperature, right? And this is for localized spins. There's no interaction between the moments. So this mean field theory can be sort of expanded. You can explain what's going on in ferromagnet or antiferromagnet if you look at the high temperature behavior of the magnetic susceptibility. So for ferromagnets, there is a Curie temperature. The magnetic susceptibility diverges at this temperature. And for antiferromagnet, there's kind of kink or peak at neo temperature. But if you extrapolate the high temperature behavior, it should diverge at some value, which is negative. So if you measure magnetic susceptibility, you can do, for example, 1/tau as a function of T minus theta. If your theta is 0, that's this case, it tells you it's paramagnetic. If this theta is positive, this will give you the Curie temperature. And then if it's extrapolated to something negative, that means the interaction is anti-ferromagnetic. Okay, so let me just recap what we can learn from this MCD measurement. MCD in general is proportional to conductivity XY component, but in this particular case, it's proportional to magnetization. You can look at the slope of magnetization as a function of magnetic fields to extract susceptibility. If you look at the temperature dependent susceptibility, you can infer the type of interaction between the local moments. And you can look at the saturation field, and that gives you an estimate of the exchange interaction strength. And this is very powerful for those moire materials or 2D materials, because we cannot do this very beautiful neutron scattering experiment to figure out the magnetic interaction here, because we are dealing with samples of about a micron square in size. And for the moire, if the period is about 10 nanometer, we're talking about 10,000 local moments. And this is what we need to measure, some technique that can access those 10,000 moments, but they are not isolated. They are embedded in tons of other materials, which will give you a large magnetic background. And this optical technique, because it has this sensitivity and this specificity, so you can probe each material individually. Okay, I should finish up quickly. I just want to give you a couple of examples. So David mentioned about the discovery of quantum anomalous Hall effects in those moire bilayers in this particular pair. So the way, cartoonish picture to think about this quantum anomalous Hall effect is pretty much just like quantum Hall, but without external magnetic fields. And you can think of it like a bulk is insulating, but you have this edge state. And you can do transport measurement, of course, to determine, to probe this. So this is like a resistance, longitudinal and transverse resistance measurement as functional magnetic fields. So the longitude, the whole resistance has this hysteresis loop, and at the zero magnetic field, it's non-zero, and the value is quantized at h/e². At the same time, the longitudinal resistance is zero because it's dominated by the H transport. So this is what you can tell from transport. And you can do the same measurements, look at the MCD, and this is the MCD measurements simultaneously done at the same sample, looking at this other aspect of the quantum anomalous Hall effect. Again, you see hysteresis loop, you see spontaneous magnetization. And as I said, you can probe each layer separately by looking at the resonance of each layer. So this is the magnetization in one layer, goes like function of temperature. And you can see here, this is roughly your ordering temperature, about 5 Kelvin with this particular quantum anomalous Hall state. And you can also do 1/, so stability as a function of temperature. It crosses x-axis at 5K. So this is our Curie temperature, right? So I probably can go on, but I probably should stop here. It's better. So I'm going to skip my second example just to give you a take-home message. So I discussed optical properties of monolayer TMDs and how we can transfer that knowledge to characterize semiconductor Moiré materials. And I talk about two things. The first is a very strong light matter interaction with excitonic effect. We can use this to probe Moiré potential, this extra peaks, things like that, the exercise we went through, right? We developed this Rieberg sensing technique to probe this correlated states. The second thing I talk about is the spin valley dependent optical selection rules. And this can be used to probe the magnetic properties of this class of materials. So with this, I would like to thank my group and collaborators. So in particular, Professor King-Fan Mak, who's going to speak tomorrow, and the former group members who contributed significantly to what I talk about, Dr. Yanhao Tan, Yang Xu. I didn't talk about Chen Hao's work on the birefringence, Shen Weijiang and Ting-Xin Li for the quantum anomalous Hall effect, and Zui Tao, who did the optical measurements, and the Bo Wen. So with this, I thank you for your attention.
Okay, questions? Someone who's not me. Okay. Yeah, go ahead. Yeah, this may be a really simple question. I'm sorry if I missed it, but.
Well, I didn't do my job well.
No. What is the electronic structure? Okay, actually, so you did these dichroism measurements at half filling or something else?
Yes.
What is the electronic structure of the Moiré electrons, and what should be their spin?
Yeah. So I showed you the without the Moiré, the single band, as single particle band structure, right?
Yeah.
So let's just forget about the second band, for example, the valence band, right? And now you introduce the Moiré potential. You can think of it just like a folding the top valence band, right? So it will be, since I talk about filling equal to 1, then just let's look at the first Moiré mini band. So this will just be like top of the valence band I showed you, right? It's cutting tiny bit of that. And the Fermi level goes through the middle of that gap.
Okay.
And if you have strong interaction, and that band is split into the upper and the lower Hubble. So that's kind of the valence band. And similar things happens to the to the electron conduction band, folding, things like that. But so we are pretty much looking at the the resonance transition. So you tune to, again, this exciton resonance. This is what we are looking at.
But I want to restate my questions. But you have local moment physics. So you have localized charge bubbles, and you have a lattice of them, and you measure the susceptibility. So those local moments have a J that you can't give because you don't know the proportionality. But that's my question. What should it be? Somebody must have already calculated.
Oh, well, so, from measurements, we can also do this, right? Because when you apply large enough magnetic fields, you can polarize all of them, and then you can use that to calibrate. And we know the density, we know this. Yes, that in that sense.
It's more of a technique question because I don't know too much about MCD. So in your slide, you mentioned it can capture sigma and y. Is it also capturing? So if I understand it correctly, it's also capturing the information of the edge states. And it's hard to imagine how, in a cartoon picture, how optically it's capturing the edge states. But kind of explaining that.
Okay. So the transport is dominated by the edge state, but this optical measurements, we're just measuring bulk. So I was just saying, in general, MCD tells us about sigma xy at the frequency of your probe in general.
But I have a very practical question. So you showed a beautiful device, nice results, but how many devices does your team have to try to make before you get one that you get such nice data? What's the yield of the preparation?
So to get Moray structure, the yield is pretty high. Pretty much, once you determine the angle by second harmonic and you bring them in, very, very high yield. Okay. But now you want to put the gates on, those. And, I showed the device structure, and typically it involves, 10, at least something like 10 transfers. And then you have to have good electro contacts, and that yield is a little bit lower. So often it's like a gate leaks, things like that. So, for optical measurements, the yield is very high. For transport, is relatively lower.
So just to give the students an idea, so like you do this, you finally get a device. Is this something you measure for 1 year, or is it, or is most of that year spent trying to get the right order? Okay. What's the kind of time scale for?
Yes, yeah. So this is something very different from maybe MB. Or sometimes you find a very good sample you measure for a long time. Our group makes those devices ourselves. So the turnaround is I would say, we make many devices, good device, of course, we would like to keep, but for each experiment, there are many devices behind. So let's put that way.
How important is twist angle disorder?
Yeah, so for homo bilayers, twist angle disorder is a very significant challenge for the field. But for the hetero bilayers I talk about, because the period is mostly determined by the lattice mismatch. So this seems to be a less problem, but of course it's still there, especially if you have string or something, so that will give you disorder. But you probably will hear from Qingfei tomorrow, despite of all those samples have good enough quality for us to study some of the ground states. So, it's not too bad. in that sense. And with optical technique, you can also pick your spot. So it's even better.
Any final student question? Yes.
Thank you for the presentation, it was very nice. So when you show one of the first slides, when you compare the adult and the adult cases, and you show some spectra. Yes, this
Maybe
this
this,
one. No,
this,
no, it's
oh,
not.
you want this one?
I think it's the next, when you show the one is, the one at the bottom.
Oh, okay.
Yeah,
That's transport measurement.
oh, I see. Yeah, because I see that in this Sharpie, there's some sort of splitting. I don't know exactly.
Okay. Yeah, so, I mentioned a little bit about the challenge to make a good electrical contacts. When you have, you can read, you probably cannot read in the back. So those are a huge, you can read it from here. It's 10 to the 8th ohm, this guy says, okay? So it's very, very insulating, and that's,
That's yours. Okay.
yeah. So those are artifacts you should not read too much into.
Last question.
So actually, I took this notes. I'm going to start with this one important one. So in your M versus T data, that's the magnetization versus temperature data versus this resistance data. So it's at 5 Kelvin, you see a lot of like resistance fluctuations. But that related to that pure temperature, is it?
Oh, okay. Okay. So I actually do not talk about the magnetic property of this, and you actually, look at my data very carefully. So, optics can give you some kind of a hint, but in this case, resistance actually is a better measurement of your insulating state. For example, how large is the gap, things like that, right? So you can look at, of course, this is not very nice because it's sitting on this large background. So tomorrow you see much nicer, better later device, later measurement results. So for example, you can tell from resistance as function of temperature, you can do, activation fit also to figure out how large the gap is, so, and you can compare to model, for example.
And why there's the users is like your magnetization versus temperature data. It's not tracing. Your magnetization versus temperature data, you show
Resistance versus temperature.
magnetization for like pure temperature, like you showed.
Oh, okay. So that's a totally different system. So this guy does not have,
It's a different question.
yeah, this guy does not have quantum anomalous law. So I can show you the magnetic measurement. I skipped, I did not talk about it. Bear with me, almost there. Yeah, so this is the measurement for this particular case, so this is 1 over susceptibility as function of the temperature. And the high temperature, it follows Curie-Weiss law. If you extrapolate this, the temperature is around -1 Kelvin. And so you can compare, for example, to, and the reason why it's, so the negative sign tells us it's an antiferromagnetic interaction. And this is due to super exchange. And you can compare to, the Heisenberg model, things like that. We can talk a little bit more if you're interested.
Okay, we better stop. So thanks, Kid. Okay, so we'll meet you downstairs. Don't line up yet for food. We're gonna take a picture and then.
Well, yeah. It's not.